Hello everyone, and welcome back to the Kohi game engine series. Today we're going to talk about the Vulkan Graphics Pipeline. Before we jump in, I'd like to take a minute and thank the supporters of the channel, starting with the partners who are Eearslya, Wensheng, and Caden. The partner is the highest tier of membership, either via YouTube or the Patreon page, so thank you very much for your support. I would also like to thank everybody else that is listed here on this screen for your support. It is greatly appreciated. If you wish to support my work, you can either join via YouTube memberships. There is a link in the description below to that, or you can take a look at my Patreon page, which is at patreon.com/Travis Roman. Alright, so the Vulkan Graphics Pipeline. Basically, in this video, we are going to talk about what the Vulkan Graphics Pipeline is, and what shaders are, and how they work from a high level. And then we will go ahead and look at what we need to do to get set up to actually compile shaders. The Vulkan Graphics Pipeline is a sequence of operations that take vertex data, such as positions or textures, and eventually output them as pixels on the screen. Now, I have a sample here on the screen of what some of that vertex data may look like. So we have things like the XYZ position, we have texture coordinates, we have normals, we have colors, and all these things I'll get into as we actually implement them, but I wanted to give you guys some sort of an idea of what vertex data might actually contain, right? So it can contain any number of things, and each individual vertex ultimately represents at least a point in space, a three-dimensional point in space, but it can represent other things as well, and these are some of those things that it can represent. The Vulkan Graphics Pipeline has multiple stages, and this is what that pipeline looks like from a very high level. This is a simplified view, of course, but this is a good place to start, in my opinion. What we have here is our flow from left to right, and our vertex index buffers. That's basically the data that's going to come in. Obviously, we'll get more into detail in that as we start to implement those things. And after that, we have something called the input assembler. Now, the input assembler is basically a process that collects the raw vertex data from the buffers that you specify, so the index and vertex buffers. And sometimes the index buffer is used, sometimes an index buffer is not used, and that's basically to allow us to reuse the same vertex data over and over again. And again, that is something I'll get into in a bit. But basically, what this does is it takes all that data that is passed in to the shader and sort of splits it up and sets it up in a way where we can actually use it in the shader program. And I'll get more into that in just a second as to what that is. So the vertex index buffers are our raw data coming in, and the input assembler takes that raw data and basically sets it up in a format that is usable for us in the next stages. So the next stage would be the vertex shader. And that is basically run for every vertex and generally applies some sort of transformation to turn vertex positions from your model space to screen space. And it also passes like per vertex data down the pipeline. So that positional data and some of the other items that I had shown you on the previous screen are some of the things that get passed in this stage. There's then something called the tessellation shader, which allows you to subdivide geometry based on certain rules to increase the mesh quality. So a couple of examples of this might be in a terrain engine. As you get closer to various bits of the terrain, you might want to add more geometry to smooth out curves and things of that nature so that it doesn't look as blocky or as, you don't have huge planes showing up, right? It's not as obvious as to what it's made out of. Another example of this might be some sort of rounded surface where as you get closer to it, you might see the faces of that surface unless you actually have some tessellation happening where there are more faces added to those rounded areas, thus making them look more round versus octagonal, for example. So after that, there is a geometry shader, which is run on every primitive. And a primitive is anything from a triangle to a line to a point. And we will cover primitives once we actually get implementing those things, but basically it can either discard or output more primitives than actually came in. So we can actually use this to generate geometry on the fly. So probably the widest use case for this will be some of our debugging utilities that we're going to be building. We'll use the geometry shader to generate some geometry for us so that we don't actually have to pass in vertex data in some scenarios. So after that comes the rasterization stage, and this basically approximates the primitives that are handed to it into fragments, and these fragments ultimately become the pixel elements that fill the frame buffer. So the frame buffer, if you recall, is the render target, and ultimately in most cases that becomes pixels on the screen. And I say most cases because sometimes we might render to a texture or something along those lines, and in that case maybe that's not rendered directly to the screen. So another important bit about the rasterization stage is any fragments that fall outside of the screen space or the frame buffer space are discarded, and the attributes outputted by the vertex shader are interpolated across fragments. So what that basically means is, let's say for example that you have one vertex that's red and then you have one vertex that's maybe a full unit away that's green. What's going to happen is as it fills in the geometry from one vertex to the next, it's actually going to interpolate from red to green. And you guys will actually see some examples of that once we actually have something up and running. One other item that's important to point out about the rasterization stage is typically fragments that are behind other primitive fragments are discarded because of depth testing. So what that basically means is if you have an object that is in front of another object in 3D space, and that object is not transparent in any way, then any object behind it is not then rendered. Those pixels or fragments would then be discarded and not actually used at that point. And there are some exceptions to this that we'll have to get into, but for now just take that at face value and we will discuss those when we get to that point. So the next stage here is the fragment shader, and this is called for every fragment that survives along the process that isn't discarded and determines which frame buffer or frame buffers the fragments are written to. And it also, at this point, determines what the color of those fragments are and what the depth values are. This can be used later on when doing post-processing type effects or things of that nature. We can use all of this data for things like that. And again, we'll touch on that when we actually get to that part, but just understand at face value for now, that's basically what it does. So basically the way that it determines color information is, as I said before, where we have that vertex data, it interpolates from one vertex to the next, and in the color example, it will interpolate between red and green. Finally, we have the color blending stage, and this applies various operations to mix different fragments that map to the same pixel in the frame buffer. And what this basically means is we can have more than one frame buffer that gets basically blended together. And this is essentially how transparency, for example, is handled, where we would draw a transparent object and then we would draw a non-transparent object behind that object and then blend the two together to actually get that what the final color of that particular fragment or pixel should be. And so this color blending stage is the stage that handles that. So if we don't have any transparency, obviously this is a pretty straightforward step. It just basically outputs the same data. But I don't know of any game engine out there that doesn't have some sort of transparency. So this will definitely be something that we will need to look into. Now, you may be asking what the difference is between these green colored stages and the yellow colored stages. And that difference is simple. The green stages are basically what is known as fixed function stages. They have predetermined functionality. The only thing that we can do is we can feed them some parameters, but otherwise how they work is predetermined and not adjustable. The yellow stages are stages that are programmable. And what I mean by programmable is we pass little programs to the graphics card for each one of these stages here, and those programs take an input and provide an output. So for example, the fragment shader takes in data from the rasterization stage and outputs color information. And the way that this is done is programmatic. So we literally write a program that gets handed to this particular stage to execute. And these programs are called shaders. Now you'll notice on all of these yellow ones, we have actually called all of these shaders except tessellation because it was too big to fit here, but this is also a shader that's available, right? So all of these are programmable via programs that are called shaders. Okay, and ultimately this gets output to a frame buffer, which then at some point will get output either to the screen or be used somewhere else in the scene as a rendered texture, like for a camera, something like that. And that is basically the overall graphics pipeline stage from beginning to end. There are other pipeline stages available that I haven't covered yet. There is a compute pipeline, but that's not something I'm going to cover here. We'll cover that later in the series if and when we need it. Okay, so I mentioned shaders, but Vulkan actually doesn't use shaders per se. It uses something called shader modules. So there is a shader module for each individual stage, as I mentioned before. So there's fragment, there is vertex, tessellation, geometry, etc. And the shader module is actually the compiled program that is fed to the graphics card. Now, I said compiled program. What exactly does this mean? So basically, there are two industry standard shading languages, and there are technically more than this, but these are the two major ones. There are two languages known as GLSL, which is GL shading language, and HLSL, which is high-level shading language. GLSL, as you might have guessed, is used with OpenGL, and HLSL is used with DirectX. So ultimately, they are two very similar languages, but different, and they perform very similar tasks and ultimately get fed in through the appropriate graphics API to the graphics card driver, which then hands them off to be processed by the actual GPU. I'm not going to go into the differences between these two, just know that we can technically use either one. For any of you that have used OpenGL, typically the way that this works is you have a file that you read in that contains your GLSL code, and then you just compile that during runtime and feed it to the OpenGL API during runtime. Vulkan does not work this way. Vulkan handles this a little bit differently. So as you can see here, I've got this third thing at the bottom called SPIR-V. So basically SPIR is an industry open standard intermediate language, right? It actually stands for Standard Portable Intermediate Representation. And what this basically is it's bytecode similar to what you might get from Java or C# or one of those types of languages, where you compile it ahead of time, and then that same bytecode is fed into the driver no matter what platform you're on. So you don't have to worry about platform-specific things in terms of how that data gets read in. You don't have to worry about big or little endian, any of that stuff. You basically compile either GLSL or HLSL through a program that outputs SPIR-V. And we are actually going to get into what that program is and how to set that up in a moment. But it doesn't matter whether you use GLSL or HLSL. Ultimately, either one of those will get compiled into SPIR-V, which is what we are actually going to read in our engine. With all of that said, we are actually going to be utilizing GLSL in this series because it's what I'm most familiar with, but if you guys are more familiar with HLSL, you can certainly do that as well. Okay, so now for a little bit more detail. So the vertex shader converts each incoming vertex to clip or frame buffer coordinates. And you can see that I've got that down here. So what this might look like in a typical scenario, if we're not rendering to a texture or something like that, let's say we're rendering essentially to the screen, quote unquote. We will have a frame buffer that is the resolution of the screen. In this case, it's 1080p, right? 1920 by 1080. And so our frame buffer coordinates is essentially the size of what that texture is that we're going to write out to, right? And so the vertex shader takes those 3-dimensional or 2-dimensional vertex pieces and converts them into frame buffer coordinates. So basically, essentially flattens them via our transformations that we provide in our matrices. And we're going to see all these things come together eventually, but I just am sort of wanting to give the high level of this now. By the time this is all output, it is output to something called normalized device coordinates, which is what the actual graphics card driver and graphics card itself knows how to deal with. And that is typically a -1 to 1 range, where 0, 0 is in the center of the screen. So just understand that there are certain cases where we will be working in frame buffer coordinates, and there will be certain cases where we're working in normalized device coordinates. So remember that there is a difference between those two. I will cover that difference again when we get there. Just wanted to point that out for now. So as I mentioned before, the fragment shader interpolates between vertices using past data, so that could be things like color or texture, and then outputs color and depth data to one or more frame buffers. Okay, so with all that explanation in mind, there are a couple of things that I want to do in this video before we actually kick off the development of our pipeline. And these are just a couple of small things in terms of tooling that I want to set up now so that we don't have to worry about this in the future. So when I mentioned SPIR-V, there is actually a program that compiles that for us, that Vulkan provides with the SDK. So if we change directory to the Vulkan SDK directory, right, and we have a look in there, there is a bin folder. So if we change directory into that bin folder and we list that out, we have a GLSLC exe right here. And this is actually the program that we want to call to compile our shader code. And this will be used with our shader modules that I talked about earlier. And so I want to sort of get a pipeline set up to call this with the necessary parameters so that we can go ahead and reference this when needed and we don't have to come back and worry about it later. So what I'm going to be setting up is something that I'm going to call the post build process. And I'm actually going to set this up for both Windows and Linux at the same time. So to do this, I'm going to go ahead and right click here and create a new file. And I'm going to call that postbuild.bat. And what this is basically going to do is it's going to do two things for us. It's going to compile our shaders, and then it is going to copy a assets folder that we're going to create. And it's going to take all the content from that assets folder and put it into our bin folder so that our engine can access it. We don't currently have that now, so I'm actually going to go ahead and create that first. So again, in the root, we're going to create a new folder this time, and we're going to call this assets. And then within that, we are going to create a new file, and we're just going to call it .getKeep. And this is just so that the assets folder makes it into the Get repository, okay? And this is where our assets are going to live. So whenever we have textures or models or anything that we need to import into the engine, this is where those things are going to live. And then our post-build process is going to take the files that are in the assets folder, and it is going to copy it into the bin folder as an assets subfolder in here alongside our executable so that we can actually work with them during runtime, okay? So our post-build process is going to take care of both of those things for us. So the very first thing that we are going to do is we're going to start off our batch file with an echo off so that we don't echo all this stuff because it's not necessary. And we're going to say if it does not exist, we are going to create in the bin folder an assets and shaders directory. Now, if this does not exist, it'll create it. Otherwise, it'll just sort of move on, right? And then the next bit, as I mentioned, is we are going to compile shaders. And we are going to compile our shaders using that glslc.exe program. So the way that we navigate to that is we have our Vulkan SDK environment variable That gives us the leading path, and then it's under the bin folder, and then it's called glslc.exe. And to this, we actually need to pass some arguments. However, before I jump into that, I do want to go ahead and just sort of run this from the command line so that you guys can see what some of the arguments are. So if we do glslc --help, it'll actually give us a listing of all the available flags that we can pass into this. There's quite a lot of them, right? So the one that we are concerned with, at least for right now, is, let me find it, F shader stage, okay? And we basically say F shader dash stage equals, and then the name of the stage. And this treats the subsequent input files as having the stage. And if you recall, the different stages that we have are vertex, fragment, tessellation, geometry, and compute. Okay, and you'll notice here that there are sort of these longer versions and shorthand versions. We're going to be using the shorthand for each one of these. So vertex is the same as vert, fragment is the same as frag. So we're just going to use vert and frag for right now. Okay, so the format that this is actually looking for is it basically takes in the options, which are here, and then the file, right? And then we're also going to want to include, it's in here somewhere, the -o, which is the output file, okay? And then, of course, a path to that. So with all that in mind, what we are going to do is, the first thing that we're going to do is we're going to build a shader for our vertex stage, right? So we have F shader stage equals vert. And then after that, we need to point to a GLSL file. So in this case, we are going to point to something in assets shaders built-in.object shader, right? And this is the name of the shader. This is what I'm calling it. This is my naming scheme. You guys don't have to follow this if you don't want. You can name it anything that you want, but this is what I'm going to stick with. However, there is a portion of this that our pipeline is going to rely on, and that is this .vert.glsl. So the .vert tells us what type of shader it is, and then the GLSL obviously is the type of file. And so this portion of it is somewhat important, but this could be anything that you want. So with that, that is our input file. And then obviously we need to tell it what our output file will be. So we use -o, and then we have here bin assets shaders, and then again built-in .object shader.vert.spv. So this SPV is what contains that, it's the file that contains the compiled bytecode of the compiled shader. Okay, and so we are hard coding the name of the shader here, and this is because at least initially we're only going to have just sort of this one built-in object shader, and so there's not really much need to build something that's a little bit more fancy than this. I'd rather keep it simple for now, and then when the need arises later on, we can extend this into something that's a little bit more fancy. But for now, let's go ahead and keep it simple, right? So the other thing that I want to do is I like to, in cases like this, when I'm running stuff with echo off, I actually like to echo a special message of my own to say what we're actually doing. So that way, as this script is running, you can tell what it's doing. So in this case, I'm just saying the original name of the file, and then I've got this sort of little arrow that I'm outputting here, and then the target name of the file. Okay, and I'm just outputting that. Okay, so we have that. We have something for the vertex stage. We also need one for the fragment stage. And again, we haven't created these files yet, but we will come back to this. So this is exactly the same name and location and all of that. The only difference is the stage is frag for fragment. The name of the file is frag.glsl here and frag.spv here. And of course, that's reflected in the echo as well. Now, should there be problems with either of these compiling, we don't necessarily want to continue with the script, right? We want to sort of echo out what that problem is and kill the script. So I actually have a line that I'm going to put in here after this first shader, which is if the error level output by this program is not 0, meaning it wasn't successful, then we are going to echo the error level, and we are going to bomb the script, basically. And we're going to do that after both the vertex and the fragment shader compilation stages, okay? And so once we are done with that, then we are ready to go ahead and move on to our asset copy. And our asset copy is actually going to be pretty straightforward. At least I think. If you've ever used Xcopy before, this should look pretty familiar to you. What we're dealing with here is we're saying we're copying the assets, and then we're copying everything from the assets directory to the bin assets directory. And this is recursive, and this is a sequence of switches that are available for Xcopy. If you're interested in that, feel free to look them up. I don't remember what all these are off the top of my head. This is just what I've been using for years. And so this handles recursion, it handles error checking, it handles overwriting of files, things of that nature. So we'll want to go ahead and perform this Xcopy, right? So this is a line that just says what we're doing, which is here. And then this is the line that actually executes it, okay? And so that will grab all of our assets and copy them over. And then of course we will simply say done at the end of the script. And that is all there is to it, right? It's a pretty straightforward script. This will get a little bit complicated once we actually start adding more shaders. But for now, since we haven't even added our first shader into this pipeline yet, I'm not too worried about it, okay? So this is the basic, this is the basis of our post-build process. Now, we have a postbuild.bat. We should also have a postbuild.sh for Linux. So I'm going to go ahead and create that. Okay, and this time I'm just going to paste the code, right? And this basically does the exact same thing. It just makes sure that the folders exist, and then it goes ahead and compiles the vertex shader, the fragment shader, and then goes ahead and copies our assets for us and says done. Okay, so this is pretty much the exact same thing as the Windows equivalent. Great. Now that we have that hooked up, one last thing that we need to do is we need to go ahead and hook this up in our tasks. Okay, so if we go into our tasks listing, we have our build engine, build testbed, build everything, and then clean everything. And we are just going to add a new entry here to the end of this list, so right here, called post build. And all this does is for Windows it calls the batch file, for Linux it calls the sh file. And we're simply just saying that the current working directory is the workspace folder, okay? And so now if we go ahead and press F1, we can go ahead and run a task, and we can say that we want to run post build. And when we do that, we actually see that our error catching is working. So it says here compiling shaders, it says which one we're compiling, and then it says it cannot open the input file because it doesn't exist, which is exactly what we expect because we haven't created it yet. Okay, so that is basically preparing us to move forward to the next part of this, where we're actually going to start building out the pipeline. So building out the pipeline is going to be probably a pretty long video, so I'm going to split this here, and next time we are actually going to start coding out the pipeline. And I should warn that you know, this is another unfortunate instance of it's going to take a long time to get through this. Not as long as it's taken us to get to this point so far, but there is a lot to consider here with the compilation of shaders, loading up those shaders, the graphics pipeline, and tying that into our current system, and ultimately getting something to show up and render on the screen. So just be prepared for that, and next time we will go ahead and get started on that. So anyway, thank you guys so much for watching. I really appreciate you guys. I hope you enjoy this series so far. I hope you're learning from it. If you like the video, please toss it a thumbs up. If you haven't already, consider subscribing. Hit the little bell notification there to get notified as to when the next video in this or other series drops, and I will see you guys in the next video.